In this video, we'll be talking about quadratic functions. We'll learn about something called the standard form for a quadratic function, and we'll also learn about some of its key features. A quadratic function is a function of the form f of x equals ax squared plus bx plus c. This almost looks like a linear function in that it has some number times x plus another number, but the big difference is that there is an x squared term for quadratics. An example of a quadratic function is f of x equals x squared. In this example, the a would be 1, the b would be 0, and c is also 0. The x squared function is a function that we've worked with before, and if you remember, its graph looks like this. The shape of this graph is called a parabola, and it turns out that in general, quadratic functions all have graphs that are parabolas. Now, there are two key features that I want to point out for quadratic functions and their graphs. First, their graphs have a special point called the vertex. The vertex is the point where the parabola changes from decreasing to increasing, or vice versa. This is also where our graph has a relative or local extremum. For the x squared function, the vertex is the origin. Notice that our parabola is decreasing before the vertex and increasing afterwards, and it's also where we have a relative minimum for our graph. The second key feature for a quadratic function is that it is symmetric. Notice that everything on one side of the vertex is mirrored on the other side. So for the x squared function here, our parabola is symmetric with respect to the y-axis. So I would say that my axis of symmetry is the vertical line x equals 0. In general, since quadratic functions have this U shape, its axis of symmetry will always be some vertical line. Now, if we want to graph a quadratic function easily, we usually don't want to work with our function in the form ax squared plus bx plus c. Instead, we have something called the standard form of a quadratic function. The standard form for a quadratic function is f of x equals a times x minus h squared plus k. So it turns out that any quadratic function can be rewritten in this way, and we'll talk about how to do that in our next video. For now though, let's talk about why we might want to write our quadratic function in this way. When we write a quadratic function in this standard form, we can see that it's just a bunch of When we write our quadratic function in standard form, we are able to recognize it as graph transformations applied to the x squared function. Let's try to identify those graph transformations. If we look within the square for our horizontal transformations, we see an x minus h inside the square. This would correspond with a horizontal shift by h units. If h is a positive number, then x minus h would be a shift to the right h units. If h is a negative number, then the double negatives will turn it into a plus, which would be a shift to the left h units. Next, we can look outside of the square for our vertical graph transformations. We see that there's a multiplication by a and an addition of k. So there is both a vertical scale and a vertical shift. For vertical graph transformations, we perform the scale first, then the shift, so our second graph transformation is a vertical scale by a factor of a. And our last graph transformation would be a vertical shift by k units. If k is a positive number, this would be a shift up. If k is a negative number, then it would be a shift down. Let's see what our graph would look like when we perform these transformations. Initially, our x squared function looks like this. Let's assume that for now h is a positive number, so we shift to the right h units. Our graph would now look like this. When we apply a vertical scale by a factor of a, that will either stretch or compress our graph, and if a is a negative number, that will also reflect our graph. So when we apply our vertical scale, we'll end up with a graph that looks something like this. Lastly, if k is a positive number, will be shifting up by k units. So taking that green graph and shifting it up k units, we'll end up with a picture like this. Let's look at our final graph on its own separate axis. So this final graph is the graph of our function f of x equals a times x minus h squared plus k. Let's now try to identify where our key features are. Let's start with the vertex of the parabola. Initially, for the untransformed x squared function, the vertex is at 0, 0. With our first graph transformation, when we shifted our graph to the right h units, our vertex moved to the point h, 0, since the x-coordinate shifted to the right h units. When we apply our second graph transformation, the vertical scale by a factor of a, well, that would take the y-coordinate 0 and multiply it by a, so the vertex does not change at all, since a times 0 is still 0. So for our green graph, the vertex is still at h, 0. Now our last graph transformation will take our graph and shift it up k units. So taking that y-coordinate, moving it up by k, our vertex is now at h, k. So when we write our quadratic function in standard form, a times x minus h squared plus k, the vertex is going to be at the point h, k. Now let's talk about the symmetry of this graph. You'll notice that everything on one side of the vertex is mirrored on the other side of the vertex. So our axis of symmetry is just the vertical line going straight through our vertex. We see here that this vertical line acts as a mirror for our graph. Everything on one side is mirrored on the other side. Now the equation of this vertical line is x equals h, since h is the x-coordinate of our vertex. So the main takeaway here is that when we write our quadratic function in standard form, we can realize it as graph transformations applied to the x squared function. And when it's written in the form a times x minus h squared plus k, the vertex of the parabola will be at the point h, k, and the axis of symmetry will be at x equals h. One last thing to talk about in this video is how the sign of a affects the shape of the parabola. When we look at the standard form for a quadratic function, remember that the a here is a vertical scale for our graph. When a is a positive number, all we're doing is a vertical stretch or compression, so the shape of our graph doesn't look much different than the shape of the x squared function. So when a is a positive number, we say that the parabola opens upwards and is concave up, and it has this sort of shape. Notice that in such a situation, our vertex h, k is a minimum for our function. So if we want to determine the range of our function, we know that the lowest y value is k, and since it goes up when we trace either to the left or right, there is no upper bound for my range. So again, if our vertical scale a is a positive number, then the range of our quadratic is going to be the interval k to infinity. On the other hand, if our vertical scale a is negative, that means we'll also have a vertical reflection. So the shape of our parabola is going to be vertically flipped from the x squared graph. So if our vertical scale a is negative, we say that the parabola opens downwards and is concave down. Its graph would look something like this. Notice that in this situation, our vertex h, k is the point where the graph transitions from increasing to decreasing. And so this vertex will be a maximum for our function. This time, if we want to determine the range, we'll notice that if we trace to the left or to the right, the graph goes down indefinitely, so there's no lower bound for my y values. For our largest y value, that will be at our vertex, and the y value there is k. So when our vertical scale a is negative, the range of our quadratic is going to be the interval negative infinity to k. So in this video, we learned about quadratic functions and their standard form. In our next video, we'll be looking at some examples of writing quadratic functions in standard form and graphing them.